Okay, let's find the absolute extrema of f of x, y on the region D, where all the ordered pairs x and y are required to satisfy the absolute value of x is less than or equal to 1, and the absolute value of y is less than or equal to 1. What does that really mean? Well, absolute value of x is less than or equal to 1, if you think about it, means x has to be between negative 1 and 1. Absolute value of y less than or equal to 1 means y is between negative 1 and positive 1. So really what it means is the region D is a square in the xy plane. So if this is the xy plane, then D might be this square right here. And its interior, where this border, this top border, is y equals 1. The bottom border, y equals negative 1. This side, x equals 1. And the left side has the equation x equals negative 1. Okay, so what we're going to do is we're going to find the absolute extrema of f over this closed and bounded region. And we're guaranteed by the extreme value theorem that these values, these extreme values of f will exist. Okay, so let's start on the interior. Let's start by taking the partial with respect, well, let me tell you what I'm doing here. We're going to start on the interior of this region. So find your critical points by taking the partial derivatives, f sub x. Okay, f sub x, if you go back and look at the function, it's 2x plus 2xy. And the partial with respect to y is going to be 2y plus x squared. And then the idea is to set the partials equal to 0 and solve this system of equations to find your interior critical point or points. I think it's just going to be one point in this case. One point that works. We're going to get a couple answers, but only one point inside the region D. So one thing I noticed from this second equation is 2y equals negative x squared. And if you think about it, there's a 2y up here. So if I go ahead and replace, well, let me circle the right thing here. If I go ahead and replace that 2y with negative x squared, that'll give me 2x. Negative x squared times another x is minus x cubed equals 0. So I'm going to solve that equation by factoring out x and getting 2 minus x squared left over inside. So I get two solutions for x. X equals 0 and x squared equals 2, which means x equals plus or minus root 2. Okay, the y values. Well, the y value that goes with x equals 0, if you just plug a 0 in here, you'll get 2y equals 0 or y equals 0. So you get a critical point of 0, 0 from the value x equals 0. And you get a critical point if you plug in plus or minus square root of 2 up here, and it doesn't matter which one you plug in, you square it out, the negative will go away if you plug in the negative root 2. And you'll end up with this minus out here times 2, so negative 2. 2y equals negative 2, or y equals negative 1. So you get the critical point, well, points plus or minus radical 2 comma negative 1. But the thing is, these critical points right here are not in D. So don't worry about them, throw them out. Okay, so what we're going to do is we're going to create a table. And this table is going to be full of all of the critical points we find. X, Y, and then eventually we'll compute f of x, y. So far, the only critical point we've found that's going to work is 0, 0. So, I mean, we could compute that now or later. It's easy enough to compute. If you plug 0 in for x and 0 in for y, you get 0, 0, 0, 4. So you can compute f of 0, 0 now or later. It doesn't matter when. Okay, now we want to talk about the border, the boundary. Now, on the boundary, if you have any sharp corners, those are automatically points you need to check as critical points. In other words, extrema can occur at the endpoints. So that means 1, 1, the upper right corner, negative 1, 1, the upper left corner, negative 1, negative 1, and 1, negative 1, the lower right corner. So this is lower left corner, lower right corner. All 4 of those are critical points. So we'll check all of those in a bit. Now, just systematically go through each border. I'm going to check the border y equals 1. So if I replace y with 1, then, okay, f of x1 becomes, well, 2x squared plus 5. Let's see if you believe that. If I replace y with 1, then certainly I'll have an x squared plus x squared here. So that's 2x squared, and then a 1 and a 4 here, so 2x squared plus 5. And I don't know, you could think of that as a one variable function. If you take the derivative of that one variable function, you get 4x. Set it equal to 0, you get x equals 0. X equals 0, y equals 1 then is another critical point. So I'm going to put that in my table. 0, 1. Okay, and then I'll check the border. So that was, well, I didn't write it down, but I should have written down that was from y equals 1. So I checked that boundary equation. Now I'm going to check the boundary equation y equals negative 1. Okay, so if I plug in y equals negative 1, I actually get a constant. Because if y is negative 1, you get x squared minus x squared here. Then negative 1 squared is 1, plus 4 is 5. I actually get 5 for the function value. So f of x negative 1 is going to equal 5. So I suppose you could consider x negative 1 a critical point or set of critical points. Of course, it just corresponds to a height of 5 on the function. Okay. So that takes care of my top and bottom borders. Y equals 1, y equals negative 1. Let's go x equals negative 1. See what we get from that. So, okay, x equals negative 1. If I plug in negative 1 for x, I just end up getting f of negative 1y equals y squared plus y plus 5. Let's see if you believe that. Yeah, if I plug in negative 1, then I'll have a positive 1 here, plus y squared, plus y, plus 4, which does get you y squared plus y plus 5. Okay, again, you could either think of this as a quadratic function, use the formula negative b over 2a to find the vertex, or just take the derivative. 2y plus 1 is the derivative of the quadratic. Set it equal to 0. You get y equals negative 1/2. So your critical point will be negative 1, negative 1/2. Put that in the table. Negative 1, negative 1/2. And then finally, if you let x equal positive 1, the right-hand border, plug positive 1 into the function. That gives you a single variable function. But I claim since you have even exponents on the x's, you'll again get y squared plus y plus 5 for your single variable function. And then if you set, well, it's going to be the same thing. Set the derivative of that equal to 0, solve, you'll get y equals negative 1/2. So your critical point here is positive 1, negative 1/2. So that goes in the table. And now it's just time to plug in these values, see which ones give you the biggest value, see which ones give you the smallest value. Well, okay, I think if you plug in 1, 1, or negative 1, 1, you're going to get the same value because of the even exponents on the x's. So that would be 1 plus 1 plus 1 plus 4, or 7 both times. If you plug in negative 1, negative 1, I think you're going to get 5. Let's check that. So negative 1, that's 1. So we're plugging in this point, negative 1, negative 1. So you get 1 plus 1 minus 1, which is, then plus 4, which is 5, yeah. So you'll get 5 here, and then 1, negative 1, you'll also get 5. At 0, 1, okay, plug in 0 for x, 1 for y, you also get 5. And if you plug in negative 1, negative 1/2, or 1, negative 1/2, I believe you get 19/4. I'll let you guys check that on your own. Okay, so out of these values, we get a maximum value of f from the two critical points, plus or minus 1, 1, and the minimum from the interior critical point. So 4 is the minimum, 7, absolute minimum by the way, and 7 is the absolute max.